So, welcome back, students. Welcome to the lecture series on signals and systems. This is a continuous lecture on elementary signals. In the previous lectures, we have defined what is meant by a unit step signal. As well, we have also seen about a unit ramp function, a unit parabolic function, and sinusoidal signals. In this lecture, we are going to study about a real exponential signal as well as complex exponential signals. So let us begin this session with this real exponential signals. A continuous time real exponential signal has a general form of x of t is equal to capital A into e power at, where both here capital A and small a are real. The parameter A actually represents the amplitude of the exponential signal at t is equal to 0. And the parameter A can be, the small a can be either positive or negative. It can be both positive or negative. It can take any value, any integer value. And depending upon the value of this small a, we get different exponentials. Let us consider if a is equal to 0. If small a is equal to 0, the signal x of t, the signal x of t is a constant amplitude for all times. As we know that x of t is given as a into e power at. Since a is equal to 0, this becomes a into e power 0, which is equal to 1. Or else simply a into 1, that is a in this case. Since we have considered that parameter capital A is the amplitude of the exponential, therefore at a is equal to 0, this becomes the amplitude of the signal. And so when plotted, you can get this signal in this fashion. T x of t for all t, generally for all t, this is a constant signal. And you could see that the exponential signal is now simply equal to a constant signal whenever a is equal to 0. Similarly, when a is positive, that is a is greater than 0, generally you will be able to see that x of t is equal to a into e power at, and x of t, since e power at is a exponential signal with small a positive, generally e power at becomes a growing exponential, and we could see the shape of this signal will be in this form. It's a rising or a growing exponential with all the values, and if at all a is equal to 0, you could see that it is simply equal to capital A. Okay, and therefore it is a continuous growing exponential signal. And similarly, if a is less than 0, if a is less than 0, if small a is less than 0, we could see that x of t is equal to a into e power at. That means a becomes negative, and this represents a negative value of exponential. Therefore, x of t becomes a decaying exponential signal, and we see the shape of this real exponential signal will be something like this: x of t, and in the same way you could see that it is something like this. Okay, at 0 it has a value of a, capital A. In the same lines, we can also define a discrete time real exponential signal. A discrete time real exponential signal exponential sequence can be defined as x of n is equal to a power n, and this is for all values of n. That means n can take any value, any integer value. If So now once again it depends upon the values of a, and generally when x of n is equal to a of a power n for a greater than 1, you generally see the shape of this discrete time exponential something like this. It goes on continuously increases with a value of 0 at a is equal to 0. It becomes sorry with a greater than 1 and n is equal to 0, you could see that it is equal to 1, and similarly goes on increasing. Since a is a positive value, and by taking the values of n uh, for positive values you could see that it is going to be increasing, and for negative values it goes on decreasing. Okay, this is going to be your x of n, the discrete time exponential signal whenever a is greater than 1. Similarly, if a is between 0 and 1, the shape of the signal changes, and we could see that x of n is equal to a power n takes the shape something like this. Takes the shape something like this, which goes on decreasing. Okay, so it decreases something like that. And for different values, similarly for x of n is equal to a power n for a less than minus 1. X of n is equal to a power n for a less than minus 1. We could see the shape of this discrete time exponential will be a rising exponential, but in both the directions generally. So on. Okay, this would be the shape whenever a is less than minus 1, and similarly if a is between minus 1 and 0, it takes a shape alternately that goes on decreasing with the values of this amplitudes in both the directions. So on. This becomes n, and this is your x of n. Actually. Okay. You could see the shape of these are the shapes whenever you could see that whenever a is greater than 1, the sequence grows exponentially something like this, and whenever a is between 0 and 1, the sequence decays exponentially, and when a is less than 0, the sequence takes alternating signs as shown in these figures. And similarly, now we shall also talk about a complex exponential. Until now, we have talked about real exponential signals, and now we shall talk about a complex exponential signal. A complex exponential signal. The complex exponential signals has a general form as x of t is equal to a into e power at. But now here capital A is once again the amplitude, but S is a that small a is a complex variable. Okay, instead previously we have considered it to be a real variable, but now it is a complex variable, and we can define something like a is alpha plus some j omega, and I now substitute the value of this a in that signal. X of t is equal to a into e power at, and therefore this could be seen as e power alpha plus j omega into t. Okay, where this can be written as a into e power alpha t into e power j omega t, where this exponential represents a real exponential, where this represents a complex exponential. Therefore, so from this definitions of Euler's identity, we can expand e power j omega t and we can represent it in the form of a into e power alpha t into cos omega t plus j sine omega t. As we know that Euler's identity says that anything which is written in the form of e power jx can be written as cos x plus j sine x. And now, depending upon the values of this alpha and omega, we get different waveforms of this complex exponential. And I would like to just demonstrate those different waveforms for you. If small a is straight away equal to 0, once again we could see that since it is represented as x of t is equal to a into e power at, and if a is 0, you could see that it is a constant signal, something like this, as we have seen in the case of a real exponential signal. Okay, this is once again a constant which is equal to a. And if a is equal to a value which is less than 0, okay, if a is less than 0, that means it represents only a purely a real value, that is and the imaginary value omega is equal to 0, we could see that it takes the shape as something like a decaying exponential, as we have seen in this case of a real exponential signal, because it simply, if omega is equal to 0, this entire part becomes 0, cos omega, this becomes 1, and therefore we are left with a into e power alpha t, and therefore this will be the same. Okay, and for alpha negative values, you could see that it is a decaying exponential once again. And similarly, when alpha is negative, you could see this. That means I have just represented that a is equal to minus alpha. Simply a is equal to minus alpha in this case, and a is equal to 0 in this case. And now I'm saying that whenever a is equal to alpha, that is a positive value, a positive real value, and where the imaginary value is 0 in that case. And you could see that it is a rising exponential in this case when a is equal to alpha, and x of t, this complex exponential, will be represented with a growing exponential. But when x of t is purely imaginary, with the value of x of t having a is equal to a purely imaginary value like j omega, where alpha is equal to 0 in this case. In such case, you could see that this complex exponential can be represented with respect to a sinusoidal signal, and you could see that it can be taking the shape something like this. Okay, assume that this is a sinusoidal signal, and for all a is equal to either plus or minus j omega, we see that x of t will be taking this shape. Okay, and similarly, whenever a is equal to alpha plus j omega, alpha plus or minus j omega, and when I say that alpha is less than 0, we see a damped sinusoidal signal which goes on decaying, something like that. It goes on decaying something. Okay. You could see such kind of a signal for alpha less than 0. And finally, we also consider one more characteristic when a is equal to a complex number represented as alpha plus or minus j omega, but here I consider that alpha is less than 0. Okay, this is for alpha greater than 0. Okay, alpha greater than 0, because we have already considered here in this previous case where alpha is less than 0. Now I am considering whenever alpha is greater than 0. Whenever alpha is greater than 0, you see the shape in opposite direction. That means it goes on increasing. Okay, the sinusoidal signal goes on increasing in this way. Okay, this will be the shape of a discrete time complex exponential sequence for various values of small a. When a is equal to 0, when a is purely real, or when a is purely imaginary. For the value of mod a is equal to 1, for value of mod a is equal to 1, generally, whenever mod a is equal to 1, the real and imaginary parts. Okay, I would like to discuss about a discrete complex exponential sequence, which actually takes a different form. Let us consider there is a discrete time complex exponential signal, which is represented as x of n is equal to a power n into e power j into omega naught n plus 5. Let us consider the shape, the complex discrete time complex exponential is of uh, this type, and therefore we can write it as a power n into. So by using this Euler's identity, I just represent it in the form of a complex number in terms of cos and sine as cos omega naught n plus phi plus j into sine of omega naught n plus phi. And for mod a is equal to 1, generally in this case, the real and imaginary parts of the complex exponential sequence are purely sinusoidal. Okay, the real and complex parts, real and imaginary parts are sinusoidal. And for mod a greater than 1, the amplitude of the sinusoidal sequence grows exponentially. Okay, the sinusoidal grows exponentially as a goes on increasing. You could see that it grows exponentially. As what we have seen in this case, it goes on, but it will be a discrete time sequence now. And similarly, for a less than 1, for mod a less than 1, in this case, it will be a sinusoidal signal, but it decays exponentially in this case. These are the various uh, cases when a takes different values. Okay, as said, when a is greater than 1, it will be a sinusoidal signal, but which it grows exponentially, and you could see the shape of the sinusoidal will be something like this. Okay, it goes on exponentially increasing. Okay, this will be the shape, as I said, whenever mod a is greater than 1. Okay, you would see that the shape of the sinusoidal goes on increasing. Okay, this envelope says all about those growing exponential in this case. That's all. If you have any doubts, you can revert it back.